I'm a master candidate from ICT, and I'm delighted to have this opportunity to share our paper with you. The topic of my presentation is BitX, Empower Versatile Inference with Hardware Runtime Pruning. DNN has been widely used in multiple fields and shown great success on numerous tasks. While the demand of large computation prohibits the deployment to practical applications, especially for embedded devices, previous works demonstrate that the network pruning is an effective way to gain the trade-off between accuracy and computation density. While all the pruning methods are based on software level and most of them face a challenge, time-consuming. Because the headroom of sparsity is not always adequate for models, some pruning approaches have to commence sparse training to create more sparsity, and tediously repeated retraining or fine-tuning is needed to accommodate the accuracy degradation. All these steps are time-consuming. When we prune the ULOV3 with network slamming, 2 to 3 days will cost on sparse training and 3 to 4 days on retraining and fine-tuning. In this paper, we propose a novel hardware runtime pruning method termed as BitX to empower versatile DNN inference. BitX is software effortless. It targets the user's binary bits, not values, and directly prunes the original DNN. No retraining, fine-tuning, or special libraries needed. The second is that it is orthogonal to the existing software pruning methodologies. BitX implements straightforward bit pruning in the accelerator. So the DNNs, either pruned or non-pruned at the software level, are suitable for BitX. It could further prune the useless bits of the software pruned DNN and obtain additional speed up. And our design can support multiplication, not only floating point but also fixed point DNN. We further propose a deep learning accelerator capable of unprecedented hardware runtime pruning to mine the maximum potential of BitX. It could obtain 2.61 to 4.82 times speed up under floating point 32 mode and up to 2 times under 60-bit fixed point mode. For the ULOV3, the speed up is 4.98 to 40.76 times higher over the original model. The accuracy degradation is negligible under floating point. For fixed point, the accuracy is even about 1% higher than the baseline. We also combined the BitX accelerator performance with other state-of-the-art accelerators. Equipped by speedup, the accelerator achieves 2 times and 3.79 times performance improvement, and I will elaborate how it is achieved next. To tackle the problem of software pruning, we rethink the parameters in a deeper perspective. We investigated the sparsity between bits and values on weights. Obviously, various benchmark DNNs uniformly demonstrate an obvious gap between the two sides. Most of the weight sparsity results are less than 1%. That's a very limited headroom for software pruning. The bit sparsity, however, are nearly 49%, which is significantly abundant. It provides an excellent opportunity of exploring the sparsity at the bit level without resorting to the value pruning. Because about 49% bits are already zeros, and removing these useless bits is definitely harmless to the accuracy. There are around 51% bit ones in the weights, which is also a very large fraction. More importantly, not all the bit ones are influential to the final accuracy. If we could identify the essential bit ones and prune away the trivial ones, the inference efficiency could be further boosted. So we further explore more opportunities for removing more bits, trivial 1 bits. We analyze the distribution of bit ones in each bit slice as shown in this figure. All the evaluated DNN exhibit an arched shape across each layer. The central bit slice owns most of the bit ones, about 40%. While all these bits are tiny, these bits are very likely to cause negligible impact to the final accuracy if they are dropped. After investigating the characteristic of bit in parameters, we intend to design a pruning method based on bit, which is used to pinpoint the essential bits and prune away the useless bits. First part of the useless bits, genetic zero bits, is easy to be exposed, and the zero-skipping mechanism could be avoided in effectual computations caused by the zero bits, which is also the main objective many previous sparsity-aware acceleration schemes target, while the second one, triple one bits, is hard to be solved, because the impact of a single bit to the whole network is not that easy to be determined. A mechanism to pinpoint the insignificant bits and prune them away is exactly the major objective in our paper. We will elaborate it thoroughly in the following parts. To clearly explain our method, we will take 6 non-aligned floating point 32 weights to be an example, as shown in this figure. We interpret their matrices, get a bit matrix as illustrated in figure A. Second, we align the matrices according to the maximum exponent. The zeros are padded in the front vacancies, just as shown in figure B. The first observation is that the aforementioned bit level sparsity is more abundant after zero padding, which provides excellent conditions for the bit level pruning. The second observation is that a large fraction of bit ones are shifted to the right direction beyond 2 sub-6 significance. We use red box to denote these bit ones in figure B. A direct consequence is that the practical contribution of these bits are pretty trivial to the final accuracy. Plumbed to bit level arithmetic could be saved to speed up the inference if these bit ones are pruned. Therefore, we prune these bits in figure C, leaving several essential ones to form the pruned weights. After explaining core concept, we next elaborate our bit pruning method. We start this from the approximation of matrix multiplication. As we all know, the product of A times B can be represented by the summation of n rank 1 matrices multiplication, and the select part of these rank 1 matrices could approximate A times B. Inspired by the idea, a bit weight matrix and activation value matrix are formed. We then use Euclidean distance of A sub I and W sub I as shown in the equation, to be the metric of selecting rank 1 matrices. Finally, the metric is determined by two factors, exponent and bit count of ith row. Bit count reflects the number of essential bit ones in ith row. For the process of bit pruning, we use designed parameter n to control the granularity of pruning. The top n bit rows with relatively larger p sub I are selected, and other rows of bit ones are pruned. Not only just a bit pruning algorithm, but also a hardware accelerator is proposed by us, which is shown in the figure. Two modules, A-alignment and bit extraction, are designed to perform bit pruning algorithm. A-alignment module is designed to align the exponent of each weight uniformly to the maximum. For the fixed point, it is bypassed. The bit extraction module is for the actual pruning. It is mainly designed to sort the shifted bit count I and select the top n largest rows. We instantiate 16 computing units to form one PE. Each CU takes M weights and activation pairs as input, which are pre-processed by the bit extraction. The figure shows details of CU. Each selector in the extractor targets one pruned binary weight. The extractor records the significance of each essential bit. Then it is used to shift the corresponding activations. The adder tree performs the final partial sum accumulation. In the evaluation, multiple modes are inferenced on cipher10 and ImageNet. Due to the limited time, we only present the results on ImageNet. This table demonstrates accuracy and sparsity performance. Conclusion is that BitX show negligible accuracy loss and improvement on some models. And we also notice there is a significant accuracy drop at n equals 4. Therefore, we choose n values in the range 10 to 6. For speed-up results, BitX exhibits promising results. Besides n, we further explore the impact of another key parameter m, and the conclusion is that m barely influenced the overall accuracy, and we choose m equals 8 for the efficient accelerator implementation. Upon m equals 8, we select two settings, n equals 10 and 6, to form two BitX instances, BitX mild and BitX wild. BitX mild has the toppest accuracy but a limited speedup, while BitX wild has little degraded accuracy but a relatively abundant speedup. When deploying it on fixed point DNN, BitX mild and BitX wild both exhibit higher accuracy than the other baselines. The accuracy improvement attain up to nearly 1%, so we concluded that BitX could precisely pinpoint the used speeds in both floating point and fixed point DNNs. For speedup results, BitX wild could exhibit up to nearly 2 times speedup over the original SqueezeNet. Although other DNNs demonstrate tiny acceleration, n equals 10 means there are only 6 bits left after pruning. The speedup is abundant. Hardware runtime pruning approach, BitX, is compatible to any software-based pruning schemes. We used the YOLO-V3 tree on Cocoa dataset as the benchmark DNN in this experiment. As shown in the table, BitX gains higher speedup than software-based pruning and considerable speedup than genetic model. We further combine our two BitX representatives with the state-of-the-art fixed-point accelerators. The speedup shows better results over other accelerators both in BitX wild and BitX mild, and the floating point results are higher than the fixed point results. Similarly to speedup results, the energy efficiency of BitX outperforms other accelerator baselines. We also study energy breakdown of BitX, and memory excesses dominate the energy consumption info system. CU energy dominates in PE only. For area and power breakdown, BitX in floating point 32 mode exhibit only 0.039 square millimeter. Overall power consumption of BitX in fixed point is higher than that under floating point. So if higher speedup is wanted, BitX in floating point mode is more suitable, and BitX in fixed point mode for lower power consumption but limited speedup. The contribution of this work are below. We propose a novel hardware runtime pruning method, BitX, to empower versatile DNN inference, and it is software effortless, orthogonal to the existing software pruning methodologies and multi-precision support. We also propose a deep learning accelerator capable of unprecedented hardware runtime pruning to mine the maximum potential of BitX. Due to its flexibility and efficiency, it could be used in self-driving cyber physics like drone robotics, embedded devices, and so on. Thanks for your attention.